Title of the module: Euclidean Domains and Principal Ideal Domains. We are familiar with both the rings Z and Z of X, which satisfies the division algorithm. Because of the significance of these rings and the power of this common property, the concept of division algorithm is worth abstracting. The Euclidean algorithm. Given A and B with B not equal to 0, we can divide A by B to get a non-negative remainder R which is smaller in size than B. That is, we can find a Q and R such that A equals QB plus R, where 0 less than or equal to R less than or equal to mod B. This fact is known as the Euclidean algorithm and we assume familiarity with it. Let us see the definition. An Euclidean domain E plus dot D, it is an integral domain E plus dot together with a function D E set minus 0 to Z plus, where Z plus is the collection of all non-negative integers such that for all A B belongs to E with B not equal to 0, there exists a Q R belonging to E such that A equals QB plus R, where either R equals 0 or D of R is less than or equal to D of B. For all A B belongs to E set minus 0, D of A less than or equal to D of AB. Here D is called a Euclidean valuation. Some examples are: the ring Z of integers can be considered an Euclidean domain with Euclidean valuation D of A equals mod A, where A not equal to 0. Let A B belong to Z and B not equal to 0. Then by using Euclidean algorithm, we can find Q and R such that A equals QB plus R, where 0 less than or equal to R less than or equal to mod B, R is non-negative, that is, R is less than or equal to mod B. We know that mod A is less than or equal to mod AB. So, D of A equals mod A is a Euclidean valuation on Z and hence Z is a Euclidean domain. Every field is a Euclidean domain. Let F be a field. Define D F set minus 0 to Z plus by D of X is equal to 1 for all X not equal to 0. Let A B be any two elements of a field F. Since F is a field, AB inverse exists. Take Q is equal to AB inverse and R is equal to 0. Then A can be written as QB plus R. Also, D of A equals D of AB, which is equal to 1 for any A B belong to F. Thus, D of A is a Euclidean valuation on F and so F is a Euclidean domain. Note that an Euclidean domain need not be a field. For example, consider the ring R of X. Here we have R of X is an Euclidean domain with the Euclidean valuation D of F of X equals degree of F of X. But R of X is not a field because non-constant polynomials have no multiplicative inverse. Let us now see a theorem. If F is a field, then the polynomial ring F of X is a Euclidean domain. The proof: we have F of X is an integral domain. Define D from F of X set minus 0 to Z plus by D of F of X equals degree of F of X for all F of X belongs to F of X set minus 0. Since degree of F of X greater than or equal to 0, D of F of X belongs to Z plus for all F of X belonging to F of X set minus 0. Let F of X and G of X belong to capital F of X. Then G of X is not equal to 0. Then there exists a Q of X, R of X belonging to F of X such that F of X equals Q of X times G of X plus R of X, where either R of X is equal to 0 or degree of R of X is less than degree of G of X. Hence, F of X equals Q of X, G of X plus R of X, where either R of X equals 0 or D of R of X is less than D of G of X. Let F of X equal to A naught plus A1x plus so on up to An x bar n, where An is not equal to 0 and G of X equals B naught plus B1x plus so on up to Bm x bar m, where Bm is not equal to 0. Then f of x, g of x is equal to a naught b naught plus a naught b1 plus a1 b naught x plus so on up to an bm x bar n plus m. Since f is a field and an is not equal to 0 and bm is also not equal to 0, we find that an bm is also not equal to 0. This implies that degree of f of x g of x is equal to n plus m. Thus, d of f of x equals degree of f of x, which is equal to n, which is less than or equal to n plus m, which is equal to degree of f of x g of x, which equals d of f of x g of x. Hence, capital F of x is a Euclidean domain. Let us see a remark. The Euclidean valuation on a Euclidean domain need not be unique. For example, consider f of x, f is a field, then d of f of x is equal to degree of f of x is a Euclidean valuation in f of x. We can define another Euclidean valuation d dashed of f of x is equal to 2 power degree of f of x. The first study of Z of I was started by Gauss, and in his honor Z of I is called the ring of Gaussian integers. And the definition of Gaussian integer is the subset Z of I is equal to the set of all a plus bi such that a comma b belongs to Z of the complex numbers is called the set of Gaussian integers. In the next theorem, we shall show that Z of I is a subring of C, and we shall determine the units of Z of I. Theorem: the set Z of I of Gaussian integers is a subring of C. The units of Z of I are plus or minus 1 and plus or minus I. The proof: let A plus Bi and C plus Di belong to Z of I. Then A plus Bi minus C plus Di equals A minus C plus I into B minus D. This belongs to Z of I, and A plus Bi times C plus Di is equal to AC minus BD plus I times BC plus AD and belongs to Z of I. That is, the Z of I of C is closed under multiplication and subtraction. So, Z of I is a subring of C. Since C is a field, Z of I is an integral domain. Suppose A plus Bi is a unit of Z of I, then there exists a C plus Di belonging to Z of I such that A plus Bi times C plus Di is equal to 1. By taking conjugate on both sides, 1 bar equals A plus Bi conjugate C plus Di conjugate, which is equal to A minus Bi times C minus Di. So, 1 equals 1 times 1 conjugate, which is equal to A squared plus B squared times C squared plus D squared, and therefore 1 equals A squared plus B squared. Hence, A is equal to 0, B is equal to plus or minus 1, or B is equal to 0 and A is equal to plus or minus 1. So, the only units of Z of I are plus or minus 1 and plus or minus I. Let us prove that Gaussian integers is an Euclidean domain under certain functions. Theorem: the ring Z of I of Gaussian integers becomes a Euclidean domain when we let the function d from Z of I set minus 0 to Z plus be defined by d of A plus Bi equals A plus Bi times A minus Bi, which is equal to A squared plus B squared for all A comma B belongs to Z, serve as a Euclidean valuation. Now, we shall see the proof of this theorem. We now have to prove that Z of I is a Euclidean domain. The function d has already been defined. Z of I set minus 0 to Z plus has been defined as d of A plus Bi is equal to A squared plus B squared. This is given already in the statement. So, clearly d of A plus Bi belongs to Z plus. So, this belongs to the set of positive integers. It is a non-negative value, and claim 1, we will have to prove two conditions in order to show that Z of I is a Euclidean domain. Let us prove the first part, which is d of x is less than or equal to d of x y for x comma y belongs to Z of I. Let us take x to be A plus Bi and y to be C plus Ei. Now, when we find d of A plus Bi and C plus Ei, it becomes product. So, product will become d of AC minus Be plus BC plus Ae times I. Now, this is of this format. So, we have already know that when it is of this format A plus IB, it becomes A squared plus B squared. So, here it is AC minus BE plus I BC plus AE. So, it becomes AC minus BE the whole squared plus BC plus AE the whole squared. So, when we expand this, it becomes a squared c squared plus b squared e squared minus 2abce plus b squared c squared plus a squared e squared plus 2abce. These two get cancelled and we are left with these 4 terms alone, and among these 4 terms we can take c squared common here, and here we can take e squared common among these 2 terms. So, after factorization it will become a squared plus b squared times c squared plus e squared. By the definition we have said that a squared plus b squared is nothing but d of a plus ib. Therefore, this will become d of a plus ib a squared plus b squared, and c squared plus e squared becomes d of c plus ei. And this is a positive integer. No? So, we have already said that any the function is defined in such a way it goes from here to z plus. So, this the codomain is a set of positive integers and d of a plus ib is a positive integer, and therefore, this term, when we leave out this term, obviously the scales are tilted and it becomes, the right hand side becomes lesser. Here until here we have equality, but here when we remove this term it becomes lesser. Therefore, d of a plus ib times c plus ei will become greater than or equal to d of a plus bi, and this is from this. And therefore, we have now shown that we took x to be this and y to be this term, and we have shown that d of x y is greater than or equal to d of x. So, one part of the Euclidean domain condition has been proved. We already proved the first part of the theorem. Now, we come to the second part, in which we have to prove the division algorithm part. So, we have to show that the second claim is this: for a plus bi and c plus ei belonging to z of I, we are supposed to prove that there exists a q naught plus q1 I and r naught plus r1 I belonging to z of I, such that this condition is true. So, a plus bi is equal to q naught plus q1 I times c plus ei plus r naught plus r1 I, where r naught plus r1 I can be 0 or it can be of this form: d of r naught plus r1 I is less than d of c plus ei. Now, this is clearly the division algorithm condition. So, we have to prove this. Now, for this particular proof we will be going in a different way. Let us assume that this q naught plus q1 I already exists. There is going to be some kind of a reverse engineering that will be done here. So, we will start from the backwards and then try to find out how this q naught and q1 will behave. So, first we assume that such a q naught plus q1 I already exists. Okay, so, this q naught plus q1 I already exists, that is our first assumption, and then we are going to talk about r naught plus r1 I. So, based on this, r naught plus r1 I will be of this form. So, we are taking from a plus bi minus, so we are bringing this on the left hand side. So, minus of c plus ei q naught plus q1 I, from here we have written this. Then let us take the c plus ei common outside. So, when we take this outside, there will not be any trouble here, but when it comes to a plus bi, it will become c plus ei the whole inverse. So, 1 by c plus ei. So, when you bring this inside, it will get cancelled and you get the original term. So, I hope you understand, it is a very simple mathematics here. And so, therefore, c plus ei is equal to a plus bi c plus ei the whole inverse minus q naught plus q1 I. Now, keeping c plus ei outside again, this term, both these terms together can be written as u plus iv, where u and v belong to the set of rationals. So, q is a rational set, and why do we say they belong to the rational set is because, see, we have spoken about an inverse term here. So, c plus ei the whole inverse. So, the behavior of these two terms together, we do not know for sure whether they are inside z, but we know for sure that they are going to be inside the set of rationals. Therefore, this u and v are going to be rationals, and q naught plus q1 I remains likewise, and here c plus ei is u minus q naught. Again, I am only clubbing the numbers together. So, u and q naught, all the real values I am clubbing together and all the imaginary values I am clubbing together. I have written it so forth. That is equal to, now multiplying on the inside, it becomes c u minus q naught minus e v minus q1 plus c v minus q1 plus e u minus q naught I. Again, I only multiplied it on the inside and I have brought all the imaginary terms together and all the real terms together. Now let us apply the function d. We already have defined the function to be d of a plus ib is equal to a squared plus b squared. So when we are applying it here, d of r naught plus r1 I will become the square of this term plus square of this term. So you can write it like this itself, c of u minus q naught minus e v minus q1 the whole square. So this real terms together are squared first and then all the imaginary terms. So this is the I standing here. So this is the imaginary terms, they are squared and they are written. So we have applied the d function here, and once again I am going to expand these terms. So it becomes c squared plus e squared u minus q naught the whole squared plus v minus q1 the whole squared and so on. How did we arrive at this? We just expanded. So when you square everything, you get the c squared terms along, you put all the c squared terms together and all the e squared terms together, take them common outside, and then you will arrive at this term. So from here we see that d of, we are supposed to prove that d of r naught plus r1 I is less than d of c plus, we are supposed to prove that d of r naught plus r1 I is less than d of c plus ei. So that is our aim here. We can see that in the claim itself we have said that this was our aim. But in order for this particular statement to be true, you have to have that this statement is less than 1. You can see that d of r naught plus r1 I is equal to c squared plus e squared. Now what do we know about c squared plus e squared? It is actually d of c plus ei by the actual definition given in the theorem. Now this d of c plus ei times this term, but I need to make this term less than this. So for that to happen, this term has to be less than 1. Therefore, from here we started in an assumption that q naught plus q1 I exists and we arrived here. So in order for this statement to be true, our q naught and q1 should behave in a certain manner, which is u minus q naught the whole square plus v minus q1 the whole square to be less than 1. But here also again we have to take this q1, q naught and q1 in a certain procedure such that u minus q naught the whole square is less than or equal to 1 by 4 and v minus q1 the whole square is less than or equal to 1 by 4. Why am I doing this? Because I want the sum of these two terms to be less than 1. So only if I take this to be 1 by 4 and this term also to be 1 by 4, when I add it becomes 1 by 2 and therefore it is less than 1, thereby satisfying this condition. So this implies that this is less than 1. Now we have spoken about q naught and q1. We have chosen this q naught and q1 in a specific manner also. Now we are left with only r naught and r1. So r naught r plus r1 I can be written as, if you take this term here, when you bring all the other terms to the left hand side, you are left with this. Here r naught plus r1 I, you know about a plus ib, you know c plus ei, q naught plus q1 I, we have shown how to pick them, and therefore they can be picked in such a way that r naught plus r1 I is equal to 0 or d of r naught plus r1 I is less than d of c plus ei. So we have chosen all these terms in such a manner that this particular statement becomes true, thereby proving our claim. So we have already proved one part of the claim. This is the second part of the claim, which is a division algorithm. This has also been proved, and therefore Z of I is a Euclidean domain. Let us talk about one more domain, which is the principal ideal domain in this session. But before going there, we will have to know about principal ideal. So the definition of the principal ideal is, let R be a commutative ring with unity and let A belong to R. Then the set generated by A equals the set of all RA such that R belongs to R is an ideal of R called the principal ideal generated by A. An ideal generated by a single element is called the principal ideal. Now the definition of the principal ideal domain is, let R be a commutative ring with 1. If every ideal of R is a principal ideal, then R is called a principal ideal ring. An integral domain which is also a principal ideal ring is called a principal ideal domain or PID. Before going on to the next theorem, we will have to recall the well ordering principle here. The well ordering principle is every non-empty set of positive integers contains a smallest member. Now we shall see an important theorem in this session. Every Euclidean domain is a principal ideal domain. It is one of the important theorems in algebra. Now we will be proving this. Let R be an Euclidean domain and let I be an ideal of R. We need to prove that I is a principal ideal in order to show that this R is a principal ideal domain. Now we shall show that I is equal to the set of all Ax such that x belongs to R, which is the set generated by A or the ideal generated by A, for some A belongs to R. So this is the definition of principal ideal domain, and this is what we are trying to prove here. Now if I is equal to the ideal generated by 0, this is the trivial case here, then the theorem holds. You can see that it holds because we take A is equal to 0. So for the trivial case it is true, but let us choose a B which is non-zero. Let B be a non-zero element and let us take it from this ideal I. It is an ideal of R. We are only now going to prove that it is a principal ideal. So we are taking a non-zero element from I, which is our ideal, and we are going to choose an A belonging to the same ideal such that D of A is minimal. Now this is possible because we have an Euclidean domain. So there is going to be a Euclidean valuation and there is an order allowed there, and therefore it is possible to choose the smallest possible value such that D of A is the minimum value. So minimal value we are going to take here, and that is going to be the minimum. So no other value is going to be less than this D of A. Keeping that aside, now since R is a Euclidean domain, one more thing is also true, that it will follow the division algorithm. Therefore there exists a Q comma R belonging to R, our Euclidean domain, such that B is equal to QA plus R, where R is 0 or D of R is less than D of A. So this is from the definition of the division algorithm. Now clearly B minus QA belongs to I. How is this? Because since A is inside I, the product of any element with A, that is QA, will belong to I. Since B is also in I, B minus QA is also going to be in the I because of the ideal definition, but we know that B minus QA is R. So from this you can say that R belongs to I. Suppose R is not 0. If R is not 0, then this particular R has to satisfy this condition, no? D of R is less than D of A. So we get D of R is less than D of A, but this is a contradiction to our earlier assumption that D of A is a minimal term here. So you have found a new term which is even less than D of A, which is a contradiction, and therefore R has to be 0. So if R is equal to 0, this implies B is equal to QA. So from here B is equal to QA, R becomes 0, so this is 0. So B is equal to QA, and therefore I have represented a non-zero B from the ideal in terms of multiples of A, and therefore you can say that I is the ideal Ax such that x belongs to R is a principal ideal, thereby making the Euclidean domain R as a principal ideal domain. Let us see a remark here. We just proved that the Euclidean domain is a principal ideal domain. Now the converse is not true. In other words, if R is a principal ideal domain of R, then R need not be a Euclidean domain. For example, consider Z of root minus 19, which can be written as A plus B times root minus 19, where A and B belong to Z, and A and B are either both even or both odd. Now Z of root minus 19 is a principal ideal domain, but it is not a Euclidean domain. Proof of this result is beyond the scope of this course, but just keep it in mind. Now let us see the relation of field, Euclidean domain and a principal ideal domain in this theorem. Let us see the next theorem. Consider R, which is a commutative ring with 1. Then we have 3 conditions. We are going to show that these 3 conditions are equivalent. That is, R is a field, Euclidean domain, and R of x is a principal ideal domain. We are going to prove that these 3 conditions are equivalent conditions. Now 1 implies 2 means that if R is a field, then R of x is a Euclidean domain. This part we have already proved in some of the earlier theorems in this session. The second part, that is 2 implies 3. R of x is a Euclidean domain, implies that R of x is a principal ideal domain. We just saw a theorem that where we proved this statement. So, there only remains one thing to be proved, which is 3 implies 1. That is, if R of x is a principal ideal domain, we need to prove that R is a field. So, let us go to the proof of 3 implies 1. Now, given that R is a commutative ring with 1 and R of x is a principal ideal domain, we now have to show that R is a field. So, in order to show that R is a field, you have to prove that every element is a unit. So, 3 implies 1. Now, let us take an element A, which is a non-zero element in R, and I be an ideal in R of x. We have already said that R of x is a principal ideal domain, and therefore, I is equal to A comma x. So, if I is the ideal generated by A comma x, it is a principal ideal in R of x. Now, since R of x is a PID, there exists an f of x in R of x such that I can be generated by some polynomial f of x, where this A and x are inside this polynomial generated ideal. Now, we shall prove the last part, which is we are going to prove that 3 implies 1, which is R of x is a principal ideal domain. I have to prove that this R is a field. So, 3 implies 1 we are going to prove now. To do that, let us consider a non-zero element A in R and let I be any random ideal generated by A and x in R of x. Now, since R of x is a principal ideal domain, every ideal is generated by a single element, and therefore, you can find an f of x in R of x such that I is equal to an ideal generated by some f of x here. But we have already taken I to be an ideal generated by A comma x, and therefore, this ideal generated by f of x will contain both the elements A and x in the ideal generated by f of x. So, there exists one g of x and one h of x belonging to R of x such that this A can be written as a product of f of x times g of x, and this x can be written as a product of f of x times h of x. Why this is so is because it is generated by f of x. Now, take this as equation 1. Since f of x times g of x is equal to a, it is a scalar value, and therefore, from this we can say that degree of f of x is equal to 0, and so f of x will belong to R. But we only started from here, f of x belongs to R of x we started, and we have ended here f of x belongs to R. Now, since it belongs to R, it only has to be some scalar value, and let that scalar value be b. So, f of x is equal to b, and take that as equation number 2. So, from 1 we show that f of x times h of x is equal to x, and therefore, instead of f of x I am substituting from equation 2 f of x is equal to b, and therefore, I get b times h of x is equal to x. But let us say you take any element 1, let us take an element 1. So, in order to show that this is equal to 1, you cannot have a polynomial here, therefore, it will only be b times some scalars, let us say c here, therefore, b times c is equal to 1 for some c belonging to R. From this we can say that b has an inverse, and therefore, b is a unit. Since b is a unit and I is equal to the ideal generated by b, how did we arrive at this is because f of x is equal to b and I is equal to the ideal generated by f of x. So, from here I is equal to the ideal generated by f of x is equal to the ideal generated by b. But since b is a unit, an ideal generated by the unit will give you the entire ring, and therefore, the entire R of x has been generated, and therefore, I is equal to R of x by 2. Therefore, 1 will also belong to I. Since the entire ring is inside the ideal generated by b, you can say that 1 is also inside I, and so 1 can be written as a linear combination of a f1 of x plus x f2 of x. Why so? Because a comma x is the ideal generated by I. This is a comma x in R of x. So, it is of this format, and hence you can write it as a linear combination of a and x terms. So, for some f1 and f2 in R of x. But here, if you are going to take 1 on the left hand side, there can be no polynomial on the right hand side. So, x times f2 of x or actually has to be 0. There is no other possibility, and therefore, 1 has to be some product of a alone. So, let us consider that 1 is equal to E into A for some E belong to R, and therefore A is a unit. From this I have proved that A is a unit. Then, so from where did we start? We took a non-zero element in R and I have shown that it is a unit. So, all non-zero elements in R are units, which implies that R is a field. The next theorem will show when the domain is not Euclidean. Theorem: let D be a domain that is not a field if there exists no B belonging to D set minus U union singleton 0, where U is a set of all units of the domain D such that for all A belonging to D, B divides A minus C for some C belonging to U union singleton 0, then D is not a Euclidean domain. Proof: suppose on the contrary, let the domain D satisfy the conditions of the Euclidean domain. Then there exists a D of B equals to minimum of all D of A such that A belongs to D set minus U union singleton 0. Since B is not equal to 0, then for every A belonging to D, there exists a delta gamma belonging to D such that A can be written as B gamma plus C and D of C is less than D of B. But by choosing B belonging to D, we have C belongs to U union singleton 0. That is, B divides A minus C for some C belonging to U union singleton 0. This gives a contradiction. The next theorem is theorem: a Euclidean ring possesses a unit element. Proof: let R be a Euclidean ring. Then R is certainly an ideal of R. So, we may conclude that R equals the ideal generated by U for some U belonging to R. Thus, every element in R is a multiple of U. Therefore, in particular, U equals U times C for some C belonging to R. If A belongs to R, then A equals BU for some B belonging to R. Hence, AC equals BU times C, which equals B times UC, which is equal to BU, which in turn is equal to A. Thus, C is seen to be the required unit element. The upcoming definitions will describe about irreducible element and prime element. Let us see those definitions. Definition of irreducible element: a non-zero, non-unit element of an integral domain is said to be irreducible if it has no proper factorizations. The definition of a prime element: a non-zero, non-unit element A in an integral domain is said to be prime if whenever A divides a product BC, then A divides one of the elements B or C. Definition of GCD: a greatest common divisor GCD of several elements A0, A1, A2 so on up to An in an integral domain R is an element C such that C divides each AI, and for all D, if D divides each AI, then D divides C. Elements A0, A1, A2 so on up to An in an integral domain are relatively prime if one is a GCD of AI. Let us finish this session with the result. The result says that let R be a Euclidean domain. Two non-zero elements F and G belonging to R have a greatest common divisor which is contained in the ideal RF plus RG. The greatest common divisor is unique up to multiplication by a unit. Number 2, two elements F and G belonging to R are relatively prime if and only if one equals RF plus RG. Every ideal in R is principal. Every irreducible element is prime. Every non-zero, non-unit element has a factorization into irreducible, which is unique up to units and up to order of the factors. Conclusion. Dear learners, let us recall the concepts once again. First, we started this module by introducing Euclidean domain with Euclidean algorithm. Then we have seen some examples and theorems, after which we moved on to the concept of Gaussian integers and principal ideal domain. We had also seen the relation between field, Euclidean domain and principal ideal domain. And we finally concluded the session by describing about irreducible and prime elements. I hope that you have enjoyed this session well. We will meet in the next session. Thank you.